very pleased with theoretical seminar in neutrino physics. Yeah.
Yeah, that's good. Yeah,
good to see you.
Nice to meet you. Yeah.
Yeah. Okay. I suppose that there should be another professor, but I don't see his name yet. Okay. I think that we have some postdoc fellows too. Here, let me introduce another professor. 하창현 교수님 들어오셨어요?
예, 들어왔습니다. 예.
Let me introduce you to Bibhushan Shakya. Here is Chung-Ang.
This is Chung-Ang. Nice to meet you.
Nice to meet you. Same.
Okay, that's it. Okay.
Sorry, do you also work on neutrino physics?
Yes, I do.
I think yeah.
Mostly experiments.
Which experiment?
Dune experiment. And we have a local experiment called NEON, which uses reactor neutrino to try to measure neutrino coherent scattering at Yonggwang. This is ongoing. Yeah. Also, I would like to join in ice cube experiment as well.
Right. Yeah.
What about you?
Oh, I do all kinds of theory. So mostly dark matter related.
Dark matter related. Yeah, I do dark matter experiment as well. So it'll be interesting to hear your presentation.
Yeah. Chung-Ang is working on cosine experiment, sodium ionide.
See.
Refuting Dhamma experiment.
Yeah. Well, not yet done.
Not yet.
It takes time, right?
Yeah. The coming years. So I think let me tell you something. So maybe you have a 1 hour for your talk, and maybe 30 minutes for discussion. Maybe. Otherwise, the talk is keep going on. So last time we took it took more than 2 hours. So I didn't say any time limit. So everybody was so tired. So maybe 1 hour and 30 minutes.
Yeah, I mean here it's pretty early. It's late for you, right? So as long as you want to keep going.
Okay, it's fine for me, but the audience, a lot of people. Let me introduce you briefly. I have your CV, so let me introduce you.
That's why you asked for it.
I know Bibhushan Shakya from several places, in particular in CERN. I think that he's a very nice guy. So
thank you.
So Bibhushan is not currently working in theory department in CERN. I think that you are moving to DESY next year, right? Yeah.
In January, yes.
In January next year. So he's moving to DESY as a STEM member. Now he's a postdoc fellow in theory group in CERN. I think that he spent some postdoc research positions in Michigan and Cincinnati and California, UC California, Santa Cruz. I think he did a nice job, and he did a lot of nice papers. And he was graduated from Stanford University, and he did PhD in Kona. So I think it's very good places, I think. So today Bibhushan is going to talk about neutrino physics and BSM. So please welcome him for our seminar.
Thank you very much. Let me try to share my screen. Is that good? Do you see the full screen?
Yes, we can.
Perfect. Yeah, so thank you again for inviting me. It's very nice to meet the group there. Good evening to all of you, I guess. So when Hyunmin invited me to give a seminar, I was confused about what topic to talk about because like I said, I do all kinds of theoretical physics work and most of my work has been in dark matter. And I was thinking about giving a talk on supersymmetry and baryogenesis and hidden sector, but I think Hyunmin was at CERN when I gave a seminar like that. And I think some other people from the group were also there. So I didn't want to repeat the same talk for them. So then I said, oh, why don't I talk about something about neutrino physics? Because that's also something I've spent a lot of time thinking about. And I think there's a lot of interesting ideas there. So today I'll talk to you about mostly physics related to extensions of the neutrino sector and what kind of interesting phenomenology you get out of these kinds of ideas. So this will be, can you see the slide changing? Just to make sure. Yes? Yeah, so this will be based on this series of papers that I wrote with James Wells and a student at Michigan, Samuel Rowland. And so for further details, you can go and look at these papers also. But to get to the main idea, right? So why are neutrinos interesting from the point of view of theory? And they're interesting, as you all maybe know, because of the fact that in the standard model, they are massless, but in fact, we know that they are not massless, right? So neutrinos are the only fermions whose mass is not explained in the standard model. And so therefore, we think that there's some new physics that comes in that's not part of the standard model that must explain neutrinos and why they have masses. They're also special in the sense that they're the only known fermions that do not carry a conserved charge. So they're not charged under electromagnetism and they're not charged under color, which are the two conserved charges in the standard model, which means that they can be their own antiparticles because there's no charge that prevents them from annihilating with themselves. But also because they don't have any conserved charges, they can mix directly with particles that are not part of the standard model. And therefore they can act as portals to physics beyond the standard model, right? And so because of this reason, we think that neutrinos are a very strong connection to BSM physics, to physics beyond the standard model. So let me elaborate on the things I've said a little bit more, mainly for the sake of students. Most of you maybe already know about these things. So in the standard model of particle physics, right, this is the field content of the standard model. And you see that there are all these fermions that come as both left-handed and right-handed components. And the Higgs binds the two components together. And that's how, through the interaction with the Higgs, these fields become massive when the Higgs gets a vacuum expectation value. The only exception to this story is neutrinos, because as you can see in this diagram, right, neutrinos only come in left-handed components because that's the only thing we have seen in nature. We haven't seen the corresponding right-handed parts. And because there is only the left-handed part for neutrinos, they cannot be gaining masses through the Higgs mechanism in the same way that the other fermions do. But this picture also tells you an obvious way to complete the picture, right? So the obvious way to complete the picture is to just add right-handed components for all of these neutrinos. And then you can do the same thing as with all the other fermions. And so right-handed neutrinos are a very natural extension to the standard model picture from this point of view. And then the question then is whether the neutrino masses in this picture would be Dirac or Majorana. And both of those are possible. So let me go through both of them very quickly. So if they are Dirac, that means that the masses for neutrinos come about in the same way as the masses for the other fermions, which means that their mass should roughly be equal to some Yukawa coupling times the vacuum expectation value of the Higgs, right? And this would mean, if this were how neutrinos got their masses, that would also mean that lepton number is an unbroken symmetry of the theory. So in the standard model, lepton number is an accidental symmetry. There is no deeper reason why it should be a full symmetry. But if it were, then this would be how neutrinos would get masses. But to explain the masses that are observed in nature, so you can see that, can you see my pointer, by the way, when I point at things?
Yes.
Okay. Yeah, so when you see this distribution of fermion masses, right? So on the left, you see that the neutrinos are very, very light compared to all of the other fermions, which means that the coupling that you need to get neutrino masses with the Higgs is a very small number. It's a number of the order of 10 to the minus 12. And from a theory point of view, this is a little disturbing, right? So you don't understand why a fundamental constant of nature should be at such a small value. But if neutrinos are Dirac and if the Yukawa couplings are this small for some reason, then this is how you would get neutrino masses. Let's think about the other possibility, which is that neutrino masses are Majorana, which basically means that you're breaking lepton number because you're saying that the right-handed component, which is, if you look at what the charges of this right-handed neutrino would be, you would see that it does not carry any of the charges of the standard model, which means it's a sterile neutrino, which is why people talk about it as a right-handed neutrino or a sterile neutrino. This right-handed partner does not need the Higgs boson to give it a mass. Actually, you can write it a mass term by itself. So you can have a mass, a Majorana mass, and that would mean that lepton number is broken. But if this were the case, then the right-handed guy would be a completely separate particle from the left-handed guy, and they would each be their own antiparticles. And so this would be the case of neutrinos being Majorana. And in this case, right, you get what is known as the seesaw mechanism. So this is a very popular mechanism to generate neutrino masses, the most popular one, which is basically saying that if you could write down a right-handed neutrino mass, a Majorana mass term, call it big M, then if that mass is much bigger than the Dirac mass that you would get by coupling the neutrinos to the Higgs, then you get a seesaw mechanism where the right-handed guy is heavy and it suppresses the left-handed neutrino masses so that their mass is given by the Dirac mass squared over the Majorana mass. And so if the right-handed guy is heavy, that makes the light neutrinos light. Even though the Yukawas are not small anymore, the Yukawas can be order 1. And as a consequence of this, there would also be a mixing between the left and right-handed components, which are now different fields. So there will be a small mixing angle that is proportional to the Dirac mass over the Majorana mass. That would be this, the mixing squared would be the ratio of those two masses. So then there's an interesting question that arises if this is true, which is what is the mass scale of the sterile neutrinos, right? Because I've told you so far that the active neutrino masses, the left-handed neutrino masses come out to be this Dirac mass squared over the Majorana mass, but it does not fix a unique value for this big M, this Majorana mass. It only fixes this ratio. And as long as you can change the Yukawa proportional to the masses, you would still get the right neutrino masses. So in principle, this big M could be anything. And you can pursue this story in two different directions, right? So a very natural choice for this mass scale is the cutoff scale for your theory, because remember that right-handed neutrinos are singlets in the standard model. A singlet naturally, from a theoretical point of view, wants to sit at the cutoff scale of your theory. So if the cutoff scale of your theory is the Planck scale or the Gut scale, if you think the standard model, the next completion is some theory of grand unification, then the cutoff scale would be 10 to the 14 GeV, right? And if this were true, and then the Yukawa couplings can be order 1, and you would automatically get the right sort of numbers for the active neutrino masses that we've measured. And so this is a very plausible choice from the point of view of theory, but from the point of view of experiments, of course, this is very disappointing because you can never hope to see neutrinos at 10 to the 14 GeV. So that's why for people who are more interested in phenomenology, there is this other regime you can go into, which is to say that you can scale down both of the numerator and the denominator in this ratio, right? So you can make the Yukawa couplings very small. And when you do that, you can also make the masses of the right-handed neutrinos very small. And so, for example, a combination like couplings of the order of, say, the electron Yukawa, which we already see in nature, and maybe not too unnatural, would give you right-handed neutrinos at a GeV scale or lighter. And so this is a somewhat unnatural choice of parameters. There's nothing inherently bad with this because unlike the Higgs, it doesn't blow up. If you put numbers, this mass is there and this Yukawa coupling there, then there's no radiative large corrections that destabilizes these values. So these are a little bit unnatural, but there's nothing wrong with values like this. But if these right-handed neutrinos were at a lower scale like this, then it is possible to see their effects in many different ways, in direct searches or in cosmology or in dark matter searches. So this is a popular thing to look into and to think about extensions of the neutrino sector that are light. By light, I mean below the weak scale and accessible to experiments. So let me tell you a little bit about this direction and what we have thought about in this direction.
Is it possible to have intermediate choices?
Sorry?
Is it possible to have somewhat in the middle?
Oh, of course, yeah. So anything between these two extremes is possible, right?
Oh, these are two extremes.
These are the two extremes, right?
Okay, thanks.
Yeah, and for example, if you want to do leptogenesis, then a popular mass scale is, I think, in the middle, around 10 to the 9 GeV, I think. So that's the region where leptogenesis works nicely. Yeah, so the range is very vast, and I'm just going to pick sort of the lowermost extreme because that's where phenomenologically it becomes very interesting. Okay, so then if you thought that right-handed neutrinos were at this low scale, then phenomenologically this is interesting because, as I told you, the left and right-handed neutrinos mix via a mixing angle, right? And so, which means that any interaction that could produce neutrinos can also produce sterile neutrinos at a suppressed rate, suppressed by this mixing angle. And you can produce it, but the right-handed neutrinos can also decay through this mixing angle. So pretty much any interaction neutrinos can participate in, the right-handed neutrinos can participate in with a suppressed mixing angle. For decays, the lifetime goes as 1 over the square of the mixing angle and the 5th power of the mass. So this is an important scaling to remember, right? So as you make these right-handed neutrinos lighter, or as you suppress their mixing with the standard model, their lifetimes become longer and longer. And in the other extreme, it goes in the other direction. So this is a crucial thing to remember that will come up again. So let me tell you in particular about the possibility that one of these right-handed neutrinos can be dark matter, because the right-handed neutrino or the sterile neutrino as a dark matter candidate is a very popular candidate. And as you can see in this distribution of possible candidates, right, the sterile neutrinos are very central. And when people think about sterile neutrinos as dark matter, they think about mass scales of around a keV. And recently, this mass scale has become sort of popular again because of a 3.5 keV X-ray line signal. And a lot of people interpret that as saying that it might be from the decays of a 7 keV sterile neutrino. But even before there were signals like this, the keV scale was a very natural mass scale for dark matter, for sterile neutrino dark matter. And it's a very natural mass scale because in the traditional neutrinos as dark matter, they were produced through this mixing angle with the neutrinos. You didn't need any special production mechanism. And this was known as the Donaldson-Withrow mechanism, or the non-resonant production method. And in this method, these right-handed neutrinos get produced because of their mixing with the sterile neutrinos. And if they are at a keV scale, and if you pick the mixing angle appropriately, they could be dark matter because they could get the right relic abundance, and also their lifetimes are longer than the age of the universe, so they don't decay away once you produce them, right? So the keV scale with a mixing angle squared of about 10 to the minus 9, 10 to the minus 10, was known to give you a very natural dark matter candidate at the keV scale. This simplest mechanism is now ruled out by data because of two kinds of observations. So on the one side, because these right-handed neutrinos can decay through this mixing angle, you can look for their decay products. In particular, they decay into a neutrino plus a photon, which is a very strong observation channel because you get a monochromatic photon signal. And so experiments have looked for these kinds of X-rays and not found anything, which gives you an upper bound on how big the mass can be or how big the mixing angle can be. At the same time, on the other side, if you wanted to make the right-handed neutrinos lighter to evade these bounds, then lighter masses tend to travel more, right? So if dark matter is lighter, but it has the same amount of energy, then it free streams over larger and larger distances. And at some point they travel so far that they will disrupt structure formation, and structures will form in a different way. And so this is something that is constrained by Lyman alpha measurements, which is basically a measure of how structures are forming in the universe. And so when you put these two observations together, the result is that this naive picture of the Donaldson-Withrow mechanism producing dark matter is now completely ruled out. And you can sort of see it in this picture where this black line is where you would get the right amount of relic abundance, right? And so you see that X-ray observations, which are these blue lines, coupled with phase space constraints, which are basically Lyman alpha, which is this pink dotted line, is ruling out most of the parameter space, or pretty much all of the parameter space. So because of this reason, Dodelson-Widrow is now no longer a viable production mechanism for dark matter. But of course, there are other mechanisms which might still be fine.
Sorry,
so let me go through.
I'm sorry. I think there is still some parameter space in your exclusion limits.
Yes, I think I picked the wrong plot to make that point. I think it is actually ruled out completely. Maybe not in this plot. Yeah, I was looking at it again.
Okay.
Sorry, yeah, so Lyman alpha is actually this brown one. Sorry, I was looking at the wrong one. Lyman alpha is this brown one, you see.
Okay.
Yeah, so then nowhere along the black line is it okay, right? So everything to the left of the brown is ruled out by Lyman alpha, and everything to the right in the blue region is ruled out by X-rays. And so the black region is then completely above.
Yeah, yes.
Sorry, yeah, I was looking at the wrong thing.
Yeah.
Okay. Yeah, so Dodelson-Widrow is not a good mechanism, but there might be other ways to produce it which might be fine. In particular, people also talked about this resonant process where if there is a large lepton chemical potential in the plasma, you can amplify the production of certain modes of these right-handed neutrinos. And even with a smaller mixing angle, you can produce the right amount of dark matter because production is now more efficient because of this lepton asymmetry. And so the result is that with a smaller mixing angle, you can get the right amount of dark matter, and a smaller mixing angle, of course, suppresses the X-ray signals, right? So then you're okay with X-ray signals. And also through this Shih-Fuller mechanism, which is this resonant mechanism, you also produce the dark matter with a colder spectrum compared to Dodelson-Widrow, and that is also better for Lyman alpha bounds. And so people think about Shih-Fuller as a possible way to get around constraints on Dodelson-Widrow, although these days the constraints are also too strong for this resonant mechanism. So this is also somewhat in trouble, but not fully excluded, I believe. So that's in the minimal scenario where you only are counting on the mixing angle with the standard model neutrinos. There are extended sectors where, so before I move on, I should say that this Shih-Fuller mechanism looks quite fine-tuned because you need a pretty large lepton asymmetry at just the right time. So there's some tuning of parameters that needs to happen, right? So people have, for that reason, also begun to look beyond the minimal scenario. In particular, if there are gauge interactions that sterile neutrinos are charged under, they can freeze out of the thermal bath in the same way as you would think of a normal WIMP dark matter doing so, right? So you can get some thermal equilibrium scenario where it then freezes out. Usually for right-handed neutrinos that are light, this process is not very efficient, so they tend to get overproduced. And so usually you need some kind of entropy dilution in these kinds of scenarios to get the right amount of relic density. And there are also some potential constraints from BBN because at that point, it turns out that these species are still doing interesting things.
What's the source of the entropy dilution?
So usually the source of the entropy dilution in these models is heavier right-handed neutrinos. So, right, so
neutrino is very light, you told me.
Yeah, so usually in these models, the simplest thing to assume is that there are 3 right-handed neutrinos, right? Just as there are 3 left-handed neutrinos. There are 3. You only want one of them to be dark matter, so only one of them needs to be very stable. The other ones are actually, you assume that they give the neutrino masses, so they are responsible for the seesaw mechanism. And so that specifies what the mixing angle needs to be. And when you take that mixing angle and see how long these heavier right-handed neutrinos live, then they tend to decay pretty late, which means that once you produce them, they will, and when the universe redshifts, they redshift as matter, right? So their relative entropy density grows relative to the entropy density. So they become a dominant source of entropy in the late universe. And when they decay, they all decay, and all of that energy gets dumped into the standard model, which dilutes the abundance of dark matter.
I see. Thank you. It's very clear.
Yeah. Sorry, was there another question?
No.
Okay. Yeah, so that was Freezeout. But then there's also this other scenario for producing dark matter, which is known as freeze-in. Right, and so the freeze-in mechanism is when the dark matter candidate is not in thermal equilibrium with the universe, in the plasma in the early universe. But nevertheless, because there are very small interactions between the dark matter candidate and some particle in the bath, you can produce it in very small amounts. And that amount does not equilibrate, but instead it just gradually builds up. And if you have the coupling just right, then you can end up with the right amount of dark matter at the end of the evolution of these particles. And so this is known as the freeze-in mechanism. It's very popular even beyond sterile neutrinos, but especially for sterile neutrinos where we know that it couples very weakly to all the other particles. This is quite a very natural way to get dark matter out of the early universe. So I will focus on the freeze-in mechanism in my talk. So yeah, so I just told you the basic idea, right? So in freeze-out, you start with some equilibrium number density, and as the universe cools, the abundance of the dark matter particle gets suppressed, Boltzmann suppressed, as the temperature drops below the mass of the particle, and then it follows this black line. At some point, the self-annihilations are no longer efficient because the expansion of the universe makes them impossible to find each other. And at that point, the abundance freezes out, right? So this is the freeze out story. In the freeze in, what happens is that you never start with this thermal equilibrium. Instead, you start with 0. But because there are some interactions, you gradually produce it, the abundance goes up. And at some point, that production process turns off. And at that point, whatever abundance you get at the end of that process is the dark matter abundance we see today. And as you can see, you can end up in the right place if your coupling strength is the same. And so this is the freeze-in idea. And so for this to work, right? So there are basically 3 things that need to be part of the theory for freeze-in to be a viable mechanism. So first of all, you need some particle that couples to your dark matter and produces it in the early universe, right? So you need, so let me call it some phi that it needs to be in the bath that couples to dark matter. Second, you need some feeble coupling between the dark matter and the parent particle. And the feeble is defined by the satisfaction of this condition. So if the coupling squared is less than the ratio of the mass of the particle, parent particle, and the Planck scale, then it does not equilibrate with the bath. And so then whatever abundance you produce from the decays of the particles, they don't annihilate away. You gradually build up the abundance, right? So, but this also tells you that then this ratio is pretty small, right? So which means that this coupling also needs to be quite small. So usually for weak scale dark matter candidates, this coupling needs to be about 10 to the minus 10. So 10 to the minus 10 is a natural number for freeze-in of dark matter scenarios. And finally, if you have a parent particle like that and you have a feeble coupling, then you need a dark matter candidate that is essentially stable, right? Otherwise it would just decay, and even if you produce it, it's not going to stay in the early universe or stay until today. And so for the third ingredient of your story, you need a dark matter particle that is effectively stable, which means that your theory needs some reason why it does not decay away. And this is a technically natural limit usually because it corresponds to a Z2 symmetry for the dark matter. So usually this emerges very naturally in a theory, and it satisfies the criteria for technical naturalness. But remember that if your dark matter is stable, it basically means there is some remnant of a Z2 symmetry in your theory, which prevents it from decaying. An important thing to note is that dark matter does not have to be at the keV scale, right? So usually when people think about sterile neutrinos as dark matter, they automatically think about it at the keV scale because of this idea of Donaldson and Woodrow. But if you were getting dark matter through freeze-in, then in principle, this could be at any mass as long as you satisfy these criteria and you get the right radical abundance. Okay, so.
Hello, by the way, I have one question. In the previous slide.
This one?
So you have this Yukawa term. Can we do the freezing from this Yukawa term?
Very good. So actually, that's a very important point that I wanted to mention, which is why I even wrote down this Lagrangian and then I completely forgot. So thank you for asking that question. So here's a simple theory, if you like, that already gives you everything, right? So this is a theory where the right-handed neutrino interacts with some scalar. And so that scalar also interacts with the Higgs. And that's why in the early universe, the Higgs will populate this scalar phi, right? And the phi, through this interaction, where X is now this feeble coupling described here. So this is a very small number. So phi decays can populate the right-handed neutrino abundance. But remember, there's also this Dirac mass term between the left and right-handed neutrinos, right? And this also has this Yukawa coupling. And so in principle, the Higgs decaying into a left and a right-handed neutrino should also give you some Friesen contribution to your right-handed neutrino abundance. And usually you can populate it this way, but then you need a large Yukawa coupling. Well, not by large, I still mean a small number, but fairly big. And it turns out that to get the right relic abundance, this coupling has to be so big that the active sterile neutrino mixing angle that it induces would be too large, and the right-handed neutrinos would just decay very quickly. So they would decay even before BBN or around BBN or between BBN and CMB. So they would definitely not survive today. So actually the Yukawa with the Higgs is not the right thing to get Friesen for dark matter. It either underproduces dark matter, or if you get the right relic abundance of dark matter, it makes the dark matter unstable. So for that reason, you do need some other particle beyond the Higgs to do this for the right-handed neutrino. So thank you for that question, actually.
Thank you.
Okay, so now that I've told you some very general things, let me just bring everything back together into the sterile neutrino story, right? So a sterile neutrino is characterized by a mass scale, which is on the x-axis here, and a mixing angle, which is on the y-axis. And so in principle, it could span many, many orders of magnitude, right? So this is where all the interesting things happen. So the first thing you would care about is getting the right neutrino masses through the seesaw mechanism. So if right-handed neutrinos were at this mass scale, then the coupling you would need to get, the mixing you would need to get the right seesaw mechanism to give the right neutrino masses is along this black dotted line, which is labeled seesaw, right? So this is the combination that gives you the neutrino masses. In this red region, these right-handed neutrinos would decay at some point after BBN and before today. And usually this is problematic because then you produce inconsistencies with observations, right? You would mess up the CMB, or you would produce too much ineffective, or something bad like that happens. So usually in this red region, there are strong constraints. It's not impossible for one of the particles to be in this region, so that's possible, but then usually you have to worry about various cosmological constraints between BBN and today. In the green region is where you would produce dark matter through the Donaldson-Withdraw mechanism. So that is okay, except you also have this X-ray or gamma ray constraint, which is the dark blue, right? Which is where these things are now ruled out by observations. What else? In the light blue region is where you can try to probe them directly. So you can produce them at various detectors on Earth and see them decay in your detector. So these are bounds coming from various, I think, B factories and even the LHC and things like that. I think the biggest one is the CHARM experiment. So this is in the blue region is where you can even see them directly in labs. So this is roughly the mapping of the parameter space for sterile neutrinos. And like I said, right, so from the dark matter point of view, this top left corner is the interesting one where you could produce dark matter through its mixing, except as I showed you earlier in this plot, the Donaldson-Withdraw mechanism is now no longer viable. But if you could come up with an alternate mechanism to produce dark matter, then in this region, it would be perfectly fine. And this also applies to all of this blank region in the bottom left, right? Because if you could somehow produce dark matter with these parameters, then if you live below the X-ray constraint, then in principle, your dark matter is not ruled out by anything. So that would still be viable. So that the left-hand corner is interesting for dark matter. The right-hand corner is what is interesting for direct searches. And now this actually lists all of the different experiments that give the constraints, right? And so as you can see, there are a lot of different ways to probe the existence of right-handed neutrinos that are sort of GeV scale or even weak scale or below, and have a significant coupling with the standard model, significant meaning about 10⁻³ And so there's many different ways you can probe for their existence. And so this corner of parameter space is interesting for direct searches. And what these searches do is basically they produce some neutrinos, and some fraction of them are sterile neutrinos. And those neutrinos will then decay in your detector, right? And the decay channels are governed by the mixing angle because it tells you how much it mixes with the neutrino. And once it mixes with the neutrino, then it decays through an off-shell Z into 3 fermions, or a fermion and a photon. And you can look for those decay channels, and that's how you place these constraints. So the top right is where things get interesting from a direct search point of view. Okay, so now that I've told you all of this, right? So let me really motivate the thing that I spend most of my time working on, which is to add new extensions to the neutrino sector. So as you've seen in the earlier slides, neutrinos being light, and by light I mean below the GeV scale, is very interesting for phenomenology. But then the mass choice is then somewhat unnatural, right? Because a keV scale or an MEV scale or GeV scale is not a natural scale in nature. So you have to motivate why right-handed neutrinos, which can have a Majorana mass that can be anywhere up to the gut scale, lives at that light mass scale. So the mass scale is something that needs some explanation. At the same time, if the mass scale is low, then as I told you earlier, the Yukawa couplings also need to be very small for the seesaw mechanism to give the right neutrino masses. So then you also need to explain why these Yukawas are tiny. And in addition, if you also want your right-handed neutrino to be a dark matter candidate, you have to figure out a way to produce the sterile neutrino in the early universe. And if you want to do freeze-in, you have to explain why you have some particle in the early thermal bath with just the right amount of mixing with the right-handed neutrino, this feeble coupling to give the right amount of dark matter. So all of these are in some sense unanswered questions, which ask whether there is a deeper structure in the neutrino sector that might explain all of these things naturally, right? And as you want to pursue this question further and also see if you get some novel phenomenology out of this process. So let me ask you the same question again, right? So why are sterile neutrinos light? So let's start with this question. And to try to answer this question, let's make use of a similar thing that we see in the standard model, which is why are neutrinos in the standard model light? And we already said that the answer was, or one possible answer was a seesaw mechanism, right? And so the answer comes in 2 parts. So the first part is that neutrinos are light because their mass is protected by a symmetry. And the symmetry is, of course, the electroweak SU2. So SU2 prevents neutrinos from getting a mass before electroweak symmetry breaking, but it also does it for all of the other fermions, and yet the other fermions are more massive than the standard model neutrinos. And so the second part of the answer to the question of why the standard model neutrinos are light is because its mass partner, which is the right-handed neutrino, is a singlet, right? So it's a singlet, so you can get a large mass for the singlet guy. You can write down this Majorana mass. And when you add these 2 things together, that the right-handed neutrino is a singlet and its Majorana mass can be very large because it's not protected by anything, you combine it with the fact that this SU2 is broken when the Higgs gets a VEV. These 2 things together give you the seesaw mechanism, which tells you that the mass is therefore suppressed by this seesaw relation, which is the Dirac mass squared over Majorana mass, right? So there are really 2 things going into why neutrinos are light. So then you ask, right, if nature does this once, can it do it again? So can the same mechanism be responsible for why sterile neutrinos are light? So what I'm imagining is that if my right-handed neutrino, so let me call my sterile neutrino a nu prime now, right, in analogy with the neutrinos in the standard model. If they are also charged, if they're also protected by some symmetry, let me call it a U1 prime, which gets broken by the VEV of some exotic Higgs field, let me call it phi, in the same way as the neutrinos, which means that the Higgs and the neutrinos are equal in charge under this new charge, so that when I write them together, it's a singlet, so that I can couple it also with a mass partner that is a singlet, just like the right-handed neutrinos in the seesaw mechanism. Right? So if this were true, then I would again get a seesaw mechanism that gives me a singlet neutrino mass, or this mass for this new prime, which is again a seesaw mass, right? It is now the Yukawa prime squared times the VEV of the exotic field squared over this large mass scale, this Majorana mass scale. And so if something this like were to happen in nature, the mass of these singlet neutrinos, these new primes, would also be suppressed because of the seesaw mechanism, just like the standard model neutrinos. And this is actually a very natural thing, because if you believe in things like string theory, right, that tells us that there are many other sectors other than the standard model sector. So there are a lot of different hidden sectors. They all have their symmetries. There are a lot of U1 primes in nature. And so it's very plausible that somewhere in a different sector, a hidden sector, there are symmetries and there are particles charged onto those symmetries. And so if a similar thing happened in some hidden sector, then it could couple to some heavy mass partner, which is basically a singlet neutrino, a singlet fermion. And so the singlet fermion could be responsible for a seesaw mechanism both in a hidden sector as well as our sector. And because these are singlets, they would live at a very high mass scale, this large M, and they would cause a seesaw mechanism to happen in both our sector as well as the hidden sector. And so this is at very high mass scales, right? So yeah, so you could even imagine that these guys live at the gut scale. But if I looked at what this theory would look like at our scales, at energies that we could probe. So if you integrate out these right-handed neutrinos, what you would get is basically some higher dimensional operators. And once you put in the vacuum expectation values for our Higgs field as well as the Higgs field in the hidden sector, this basically looks like a seesaw mechanism between our neutrinos and the fermions in the hidden sector, which I call nu prime. And this basically looks like the seesaw mechanism, except that the partners are now these nu primes, right? So at a low energy, the picture I showed you earlier actually reduces to a low energy seesaw framework, where you would think that these nu primes, these exotic fermions in a hidden sector, are the mass partners for our neutrinos. And they couple with some effective Yukawa coupling, which is given by this ratio of this hidden sector VEV divided by the mass of the mediator neutrinos. And they would get an effective mass, which is basically the seesaw mechanism in the hidden sector. So at low energies, this picture breaks down to a low energy seesaw mechanism where the hidden sector fermions are the mass partners. So any questions?
So in your second part, you should have a similar structure as the standard models. So in principle, if your right-handed neutrino have some charge, then your new scalar phi should all the same charge of this right-handed.
Yes, right. Exactly. So that's the special thing about the neutrinos, and that's what gives the seesaw mechanism. And so that should also happen in the other sector. Yeah. Mm-hmm.
Is there
Okay, so
twin Higgs model?
Yeah.
This hidden sector.
Yes. In principle, yes. Let me comment about that later when I start talking about the mass scales. Yeah, so there you run into some trouble with cosmology usually, but otherwise, yes, definitely. Yeah, so the implications of this picture, right, are that you not only have mass partners for the neutrinos, you also have an extended sector of its own that has its own symmetries and particles, right? So there are these sterile neutrinos, and so I will refer to them as N from now on. I'll just forget about the mediator that couples the two sectors. So as far as I'm concerned, these fermions in the hidden sector are the sterile neutrinos that gives a mass, well, that we look for in experiments. But there are really some exotic fermions that are part of a hidden sector that get light masses because of a seesaw mechanism. But then there's also a scalar in that hidden sector that should get a VEV and break that symmetry, right? So there needs to be a Higgs boson in a hidden sector. And depending on whether that symmetry is global or local, you also have a Goldstone boson or a gauge boson that is part of that extended sector. So then, well, yeah, so then this is interesting because there's now a much more extended sector where you can try to do additional things, and you can also try to get interesting phenomenological signatures, right? So then let's ask the first main question, which is, if there is a symmetry in the hidden sector, what scale do you break it, right? So what's the sort of the right scale to break it if you want interesting phenomenology? And if you fix as your handle the fact that our neutrinos have a mass scale that's sort of EV scale, then you get that if you want your right-handed neutrinos to be at a KeV scale, then you need to break the symmetry at about tens of TeV or hundreds of TeV. If you want these right-handed neutrinos to be at a GeV scale, you want to break it at about 100 PeV. So these are very high scales, which give you really light sterile neutrinos. And that's sort of reminiscent of how things work in the Standard Model, right? So the Higgs scale is at 100 GeV, and yet your neutrino masses are at an EV. So there's a natural separation of scales because of the seesaw mechanism. And the same thing happens with a hidden sector. So even if you want new particles, which are these sterile neutrinos that are at a keV scale or a GeV scale or MeV scale, you don't necessarily have to have any interesting dynamics, any symmetry breaking at that scale. It could actually be at a much higher scale. Right? So in this picture, it could be at above the TeV scale, even at the PeV scale. And one thing you might see this connecting to is, for example, ideas of split supersymmetry, right? So in supersymmetry, there's this idea that if the mass spectrum is split, then the natural scale for breaking of supersymmetry is at about the PeV scale, which is this idea of split supersymmetry. And if that is true, then there's also already a reason for nature to have some interesting things at this scale, right? So if supersymmetry is broken at that scale, you can imagine that that is what triggers the breaking of this particular symmetry that then gives you light exotic sterile neutrinos. But it doesn't have to be that scale. So this picture came about because I insisted that the mediator between the two sectors was at the gut scale, which is also not necessary, right? So if I want my mediator to be at a different scale, or if I want my neutrinos to be at a different scale, then accordingly you would get that the symmetry should be broken at a different scale. So instead of the keV scale, if you were interested in very light sterile neutrinos at an EV scale, and your mediators were still at the gut scale, that would mean that you had a new symmetry that needed to be broken at a few hundred GeV, right? And a motivation for an exotic sector that has the same mass scale as our sector is, of course, the twin Higgs, like Hyunmin said. But if you try to put this picture into the twin Higgs story, you would also get that the neutrinos in the twin sector are at an EV scale. And because the twin sector has this large Higgs coupling between the two sectors, cosmologically, this is dangerous because the other sector thermalizes in the early universe, which means you have these EV scale neutrinos floating around, and usually they produce too much dark radiation. And so these are in trouble with ineffective, which is why people usually get rid of the neutrinos when they talk about twin Higgs sectors. But in principle, you could try to do something like this and get twin neutrinos. The EV is too dangerous. So usually when people do this in the twin Higgs model, they put the twin Higgs web at a slightly higher scale so that your right-handed neutrinos or your twin neutrinos are no longer at an EV scale, they are at an MEV scale where things become okay with an effective. At the same time, if you were okay with bringing down the mass of the mediator between the two sectors, and you still wanted your neutrinos to be pretty light, right? These singlets to be pretty light, then you would also be talking about breaking of the symmetry at a few hundred GeV scale. And this is an interesting thing to look at if you are interested in collider signatures for this mediator, as well as dark matter signatures for the fermion. And so you can think of many different possibilities depending on what exactly you were interested in getting out of this picture. Okay. So let me in particular now look at each component of this extended sector and think about interesting things that can happen because of that. Right, so let's start with the fact that there is now a Higgs in the other sector. Why is that interesting? And that turns out to be interesting because, so let's look at the scales before the symmetry in the hidden sector is broken. Right, so if I've integrated out my mediators, this heavy N, then what I basically get is these cross terms between, so this is the lepton doublet and the Higgs doublet in our sector. This is the fermion and the scalar in the hidden sector, right? So you get these higher dimensional interactions that connect particles in the two sectors, and they're now suppressed by the mass scale of this heavy neutrino you've integrated out. So you get these higher dimensional interaction terms. You also get a higher dimensional interaction term, which is basically giving you the mass for the sterile neutrino. So this is basically the analog of the seesaw in the hidden sector. And so you would end up with these higher dimensional operators above the breaking scale. Below the breaking scale, once you put in a VEV for the scalar, what you get is that this gives you an effective Yukawa term, right? And this gives you an effective mass term for the neutrino. But what it also gives you is some interactions to freeze in dark matter, right? So like I said, there's this term, which is coupling two dark matter particles to two scalar particles. Once you put in a VEV in one of them, you get this decay channel, which is that the scalar can now decay into 2 right-handed neutrinos, right? So this is already giving you condition 1 for the freeze-in picture that I showed you earlier, which is that there's now a scalar in the early bath that can decay into 2 right-handed neutrinos. If you look at what the coupling for this process is, you see that the coupling for this process is this, because this coupling is an effective coupling that comes out after you put in a web for the scalar, right? And that coupling is basically some Yukawa coupling in the UV theory times the web of the scalar divided by the mass scale of the mediator that couples the 2 sectors. And like I told you, this mediator can be very heavy. It can be at the gut scale, whereas the intermediate scalar is at a lower scale, right? So it could be PeV scale or TeV scale, which means that there is a natural reason why this effective coupling is suppressed by many orders of magnitude. So this then also satisfies the second condition for the freeze-in picture, which is that you need a feeble coupling between the parent particle and the dark matter, right? So this is a way to understand why there is a small coupling in the theory that gives you freeze-in production. And when you plug in numbers, you indeed see that you get the right amount of relic density for this singlet fermion to be dark matter. And so, for example, if you want a GeV scale dark matter candidate, that tells you that the symmetry needs to be broken at around the PeV scale. So in the split SUSY picture, this is something that comes out pretty naturally. And so additionally, you assume that the Yukawa coupling for this particular neutrino is suppressed for some reason, right? So you need this Z2 symmetry to stabilize your dark matter. But this is, again, a technically natural limit because you just assume that this mediator between the 2 sectors for some reason doesn't couple very well to one of the particles in the hidden sector. So this is a very natural way to get the right amount of relic density for dark matter. This is just the IR component of the dark matter story, because there's also a UV component, right? Which is even before you break the symmetry, there are these higher dimensional interactions which already produce some dark matter, because through this interaction, for example, a neutrino and a Higgs in our sector could annihilate into a neutrino and a Higgs in the hidden sector. And so this interaction is possible, but it's very suppressed because of the presence of this cutoff, this M star. So this is, again, a very feeble process, especially if this mediator mass scale is something much heavier than the temperatures in the early universe. And so again, you see that these interactions will not bring the hidden sectors in equilibrium. And so this is a way to do a freeze-in process in the early universe, in the UV. And because these are higher dimensional operators, you get some dependence on what the temperature of the bath was in the early universe. But if the reheat temperature in the early universe was sort of at the right scale, then these UV interactions by themselves could already produce dark matter through the freeze-in mechanism. So there are both a UV and an IR component to the dark matter production story. And depending on what the parameters are, so this plot is basically meant to tell you that depending on what the parameters are, either the UV part or the IR part can be the dominant production source, right? So here the axes are the mass of the scalar, the mass of the parent particle. Now we're looking at the PeV scale, and on the y-axis is the reheat temperature in the early universe. And if you are living with a large reheat temperature, that means that the UV process is very much stronger, right? So the blue is where the UV is producing the dominant component of dark matter. If the reheat temperature is low, that means that the UV is not very strong, and the IR, the decay process, is producing most of dark matter, which is what happens in the orange region or the yellow region.
I'm sorry, can I ask a question?
Please.
The UV production is motivated by to solve the small coupling in IR production. Yeah.
No, it's just something that happens, right? So it is part of the theory.
Yeah, yes. So what I want to say, you can just propose the UV production at the very beginning, so there is no need.
Yes.
So I'm a little confused because the IR production has some small coupling problem. So you propose a higher dimensional operator, then there is a UV production. Yeah, am I right?
Sorry, yeah. Sorry, I lost you for a second, I thought.
Okay. Okay. Well, thank you. There's no problem. Okay.
So regardless of whether the hidden sector particles are thermalized or not, so as long as the temperature is high enough, you will produce some UV. The IR component, let me try to go back to that slide. So this requires the scalar to be part of the thermal bath. And so that requires some additional interaction that produces them, right? So some quartic Higgs coupling between the scalar in the hidden sector and our sector. So the IR part has an additional assumption that needs to be satisfied, namely that this thing needs to be thermalized. The UV does not. So in some sense, the UV is more minimal. Does that answer your question? I think I even missed the question, so sorry.
Okay, but I have no question. I just I'm just curious about the motivation of this new symmetry breaking, because you say the new symmetry breaking is introduced to solve the small coupling problem.
Yes.
But if you introduce a higher dimensional operator, then the IR production is irrelevant.
Absolutely. Yeah.
So it seems no motivation is lost during this calculation.
Yeah. So the motivation is only necessary if the reheat temperature were low for some reason, right? So if the universe never reheated to these temperatures,
a very low reheating temperature, then the IR production is dominant.
Right. Yeah. So that's where you would need it. Absolutely. Yeah.
Thank you very much.
Excuse me. May I ask a question?
Yes, please.
So I'm wondering about the top right corner of this figure. It's still, maybe I missed something, but suppose the phi is kind of mediating, for instance, a pair of Higgs annihilate into a pair of dark matters through S-channel exchange of phi at high temperature. And if that is the case, the M phi is still lower than reheating temperature. So the annihilation cross section at high temperature is still suppressed. So I'm wondering why, in that case, the UV looks dominate over in a dark matter abundance. Because UV reaction is suppressed by the light mediator compared to the heating temperature.
Yeah, so you need the heavy right-handed neutrino, right? This N that was coupling the two sectors, that needs to be in there somewhere just to be able to go from the hidden sector to our sector, right? So you always get this 1 over M star suppression. And so the interaction that, yeah, so the process you're talking about maybe contributes, but the process that is driving this UV production is actually the hidden sector Higgs and the hidden sector neutrino. Sorry, our Higgs and our neutrino going through this heavy mediator N, this fermion, into the hidden sector scalar and the hidden sector N. So in addition, if you also have a scalar quartic, so a phi squared h squared, then it is true that Higgs going into the heavy scalar into two NNs, that would also be a contribution. And
I see.
Yeah, so then actually you're right. So in some parts that might be driving the process. And so that is not taken into account in this picture. No. Yeah,
I see.
absolutely.
I see.
Yeah, so that would be an additional contribution. Yeah. Thank you. Okay, so we said we're not natural and needed an explanation. And so in this picture, they all have an explanation, right? So the first question was, why are the Yukawas for the seesaw mechanism for the active neutrinos, why should that number be 10 to the minus 7? In this picture, that number is 10 to the minus 7 because it is this effective coupling that you get after this U1 prime symmetry breaking, and it is actually the VEV of this hidden sector scalar divided by the gut scale. And if there are 7 orders of magnitude between these two scales, then you get a Yukawa that's 10 to the minus 7. We said we needed an explanation for why masses of these singlet fermions, these sterile neutrinos, should be small, right? And in this picture, they're small because they also get a seesaw suppression in their mass. Their mass is hidden sector scalar VEV squared over the gut scale. And if this scale is intermediate, then you get a seesaw. And that's why these singlet neutrinos are light. That's why they're at a KV scale or a GeV scale, right? And we also said we need an explanation for if this right-hand neutrino is dark matter. We need an explanation for why it gets produced in the early universe. In the spectra, it gets produced in the early universe because one, there are some UV contributions that can already produce them, but also there's the scalar that is necessary because it breaks this exotic symmetry, but that scalar also has a decay channel that can populate dark matter, right? And we also said if it's a freeze-in story, we need an explanation for why this coupling is a feeble coupling. And again, we saw that that coupling was a feeble coupling because it is an emergent coupling that comes about after the symmetry breaking, and so it is a suppression of these two scales again. So in this picture, all of these unknowns are explained by this fundamental idea that you break an intermediate symmetry, you break an exotic symmetry at an intermediate scale, and it's suppressed by the mass scale of these heavy mediators, right? So perhaps this is a somewhat nice explanation for why these small numbers are small. So that's what the Higgs was there for. Let me now sidetrack a little bit and think about what other things can happen if your underlying theory is also supersymmetric. So if supersymmetry is also a part of this extended theory, then what kind of interesting things can happen for neutrinos? So the main thing with supersymmetry, right, in terms of phenomenology, is that it gives us, for every particle, it gives us a superpartner, and the superpartner shares the same properties as the parent particle, right? And so in this case, in addition to the scalar, you would also get a superpartner, which is a fermion, and in addition to the right-handed neutrino, you would also get a superpartner, which is a sterile neutrino. And usually these particles will share the same properties because they are part of the same supermultiplet. So let's look at what this superpartner of the dark matter candidate would do, right? So it's a scalar. Its mass should be heavy. Mass should be at the scale of SUSY breaking. In the early universe, it would also get produced by the same process that populates dark matter. So the scalar, in addition to decaying into neutrinos, can also decay into these neutrinos, right? Because it can come about through some soft term or something like that. So it will get produced in the early universe. The interesting thing to think about is how it would decay. And to think about how it would decay, remember that your dark matter candidate in this theory has some remnant Z2 symmetry that makes it stable, right? Which means that in principle, it doesn't interact much with anything else. It needs two copies of itself for any meaningful interaction. In the supersymmetric picture, that would mean that the sterile neutrino, because there is this Z2 symmetry that the dark matter is charged under, the superpartner would also inherit this Z2 symmetry, which means that any interaction that it has should preserve the Z2, which means that anytime the sterile neutrino decays, it has to decay into a sterile neutrino, because that's the only way to transfer the Z2 charge, right? So any decay process it has must involve a dark matter guy, which is basically saying that the superpartner, when it decays, will always produce a dark matter. And there are two interesting things to note, right? So one is that it always produces a dark matter. The other interesting thing to note is that the sterile neutrino tends to be very long-lived because all of its couplings are very small, just like the dark matter candidate. So the driving, just like the driving thing for the dark matter was this feeble coupling, the driving thing for the sterile neutrino would also be some supersymmetric counterpart of this feeble coupling. So its decay is dominated by this small number, which means that its decay is very slow. And so it tends to be very long-lived. When it's long-lived, it tends to dominate the energy density of the universe. And when it decays, it produces the bath, because this mass is now much heavier than the temperature of the thermal bath, right? Which is visually, that just means to say that now there are multiple populations of dark matter that are being produced. So one is the normal picture of freeze-in, where I had the scalar, it decayed into dark matter. But if the underlying theory is supersymmetric, now you also have a superpartner that also decays into dark matter. The superpartner has a much longer lifetime, right, because of the structure of your theory and because of the fact that they're supermultiplets. And because of that, the sterile neutrino decays at a much later time, which means that it produces a subcomponent of dark matter that is much hotter. And the interesting thing about the freeze-in mechanism is that even the dark matter population itself doesn't interact with each other that much, which means that these two populations that you produce don't actually mix together. So they remain as two separate components. And so even today, if you could measure the dark matter spectrum, you should be able to see that there are these multiple distinct contributions floating around. So if you could measure the momentum distribution of dark matter, you would see something like this.
What is the scale of atom in your?
What is the scale of the A term?
that determines the decay of the scala into sterile.
So the decay is actually not determined by the A term, right? The A term is all scalars, so it doesn't involve a fermion. The decay is
the sterile neutrino. Sterile sub-neutrino is also dark matter, right?
No. So that can decay because, so for example, right? So you have this Yukawa coupling, which is the left, right, and the Higgs. So then you can switch two of them so that the sterile neutrino decays into a Higgsino, right, and a neutrino.
I see. It's a long-lived product.
Yeah, so it will decay, but the decay will be very long-lived.
Okay.
Yeah, so that's why you would get this. So you would get the usual contribution for dark matter, which is this biggest bump. But at a later time, you would also get the second population because of the fact that its superpartner is decaying at a late time. And so you would be able to get the second bump, right? And once you produce these two different bumps, these two different populations of dark matter, they don't mix with each other because the Freezeout coupling is so small and the self-interactions of neutrinos are so small, of sterile neutrinos are so small. So you get this extremely non-trivial distribution for dark matter that will persist even at later times. And you can even push this peak a lot, so you can really make the right-handed superpartner very long-lived. And the second peak can actually act like radiation at late times. So here on the right-hand side, you get this plot, which is right, the mass of the dark matter guy on the x-axis, the mass of the superpartner on the y-axis. So if the superpartner is really, really heavy and it decays very late, then this population is very energetic. And so what are plotted in the colors is the contribution to N effective at BBN. And you see that N effective contributions of the order of 0.1 are possible in a very consistent way. So a small component of dark matter could even be acting like dark radiation at the time of Big Bang nucleosynthesis, and you would actually be able to measure this at some point.
Excuse me. May I ask a question?
Yes.
So I'm wondering about the fermionic pattern of phi. So it's it should have a mu term as well. And if it is right, can it be a dark matter as well? Yeah, on top of this neutrino.
I think it would also decay though, right?
How? Well, if the well, I don't know how can it be decaying?
So it can decay into a neutrino and a neutrino, for example, right? So I'm
but you're taking yeah, but you're taking the breaking scale a bit higher than the you know, those fermionic scales. Well, are you assuming that the mu or pi is also like?
But even if you can always go through off-shell things, right?
Right. So this neutrino goes to sterile neutrino plus lepton, just a standard lepton.
Something like that. Yeah.
I see.
Yeah, but
so it also produces. Yeah, but nevertheless, that channel also gives us dark matter additional production channel.
Yeah. No, absolutely.
Right.
Yeah.
I see.
Yeah.
Okay, I see. All right.
Yeah. So there are several contributions, and I think secretly, I'm just assuming that they're all of the same order. So then you just look at one, and then there might be order one corrections to that from other things.
I see. Yep, thank you.
Sorry, I'm not sure about this additional production from sterile neutrino decay. So you said the sterile neutrino will decay into Higgsino and lepton.
No. The sterile neutrino will decay into the dark matter guy, the sterile neutrino plus Higgsino.
Plus Higgsino.
Yeah.
Okay.
And the Higgsino, yeah, so depending on what you do with our parity, then the Higgsino might be also dark matter, or it can decay later on. Right?
Okay, I cannot, because I don't see the Lagrangian for the cosmetic model, so I'm trying.
So it's basically, it's basic, I would say it's basic let me think. Yeah, so it's basically this, and then you just take the super partners of these two.
Okay. The sterile, okay, sterile neutrino.
Yeah, and yeah, so this can go off shell, I think.
Okay, I see.
Yeah. So given that I think I've been talking for an hour, should I try to wrap up, or is it okay to just keep going? How much time should I aim to spend? I think you're muted.
How much time do you need?
I think 10 more minutes.
Okay, yeah, I think you'll be fine.
Yeah, because, yeah, so that's basically the main ideas I wanted to tell you about the part when supersymmetry is relevant. But so far, I've just been telling you about things that are very heavy and only relevant for very early universe, right? Just production of dark matter, maybe. So then it's interesting to think about, can there be things that are light in addition to the sterile neutrinos? So let me think in particular about the case when the symmetry in the hidden sector is a global symmetry, so that when you break it, you get a light Goldstone in the theory. So let me start by warming up by talking about the Majorana model, because that's a very popular model where there's a Goldstone in the sterile neutrino sector, right? So in these Majorana models, the story is that you have a right-handed neutrino that gets a Majorana mass when you break a symmetry in that sector. And the symmetry breaking happens because of this term. So you have two right-handed neutrinos that couple to a scalar that is now called sigma in this particular paper. And so the sigma gets a VEV, sigma 0, which is what gives you a Majorana mass for these fields. But because the symmetry is a global symmetry, you also get a component that is the Goldstone, which is called the Majorana in these models. And so the sterile neutrinos will get a mass that is proportional to the VEV of the field, which is F, times this coupling for this term, right? But then you also get this Goldstone, which gets a small mass from gravitational effects or from explicit symmetry breaking terms. So it's not completely massless, so it's a pseudo Goldstone. But it's a very light thing because its mass is suppressed by M Planck, right? So compared to the right-handed neutrinos, it is much, much lighter. This Goldstone can couple to neutrinos as well as sterile neutrinos. And so you get very exotic decay channels, like the right-handed neutrino can now decay into a neutrino plus a Goldstone instead of your usual channels. Or the Goldstone, if it's heavier than our neutrinos, can also decay into our neutrinos. And people have looked for various ways to test these kinds of things, right? And another important thing to notice is that the coupling of the Goldstone is suppressed by this ratio, which is the mass of the neutrino divided by the symmetry breaking scale. So usually the couplings of the Goldstone are very, very light, and the Goldstone itself could be dark matter in some models. So this is the usual Majorana story. So in the story, I've been telling you things that are a little different, right? Because, so let me tell you first, what are the things that are still applicable. So when you break a global symmetry, it doesn't have to be the lepton number. So in the Majorana story, I should say, right, that the symmetry you're breaking is lepton number. So the Majorana is the naming itself, right, tells you that this is the thing that is giving you the same thing that gives you Majorana mass as right-handed neutrino. So it's breaking lepton number. But any symmetry, global symmetry when broken, it doesn't have to be lepton number, will give you a Goldstone, which is initially massless, but it gets a small mass because of global effects from gravitational effects. So it's a mass that is roughly proportional to the cube of, or F cubed over M Planck is the mass squared of the Goldstone, right? So it's a mass that is suppressed by the Planck scale, and it's proportional to the symmetry breaking scale. And it will couple to all of the neutrinos through some coupling that is proportional to the mass divided by the symmetry breaking scale. So in the picture I was showing you earlier, there is also a Goldstone if the symmetry is global, and it differs from the Majorana in these different ways, right? So first of all, the symmetry you're breaking is some exotic symmetry in a hidden sector. It is not lepton number, right? Because lepton number is already broken when you write a Majorana mass term for your heavy mediator particle. So it's broken close to the gut scale. So the symmetry you're breaking, this U1 prime, is something else which is broken at a lower scale. If the symmetry breaking scale is F, as in the Majorana, or as in the Majorana models, then the mass of the pseudo goldstone is the same, which is just F cubed over M Planck, as I told you earlier. But the crucial difference here is that the sterile neutrino masses are now different, right? In the Majorana model, the neutrino mass scale is linearly proportional to the symmetry breaking scale because it's coming out of this interaction term phi and n. But in the story I was telling you earlier, the sterile neutrinos, remember, are light because of the seesaw mechanism in the hidden sector. So their masses are also small. And so the crucial difference from the Majorana model is that in the story I was telling you earlier, the sterile neutrinos and the pseudo goldstone are both very suppressed masses. And in principle, they can be of the same order, right? In the Majorana model, usually the sterile neutrinos are much heavier than the goldstone. In the hidden sector model I was telling you about, the two masses can actually be at the same scale. And so this might be interesting for cosmology or for other kinds of signatures. So let me briefly tell you about what happens when the goldstone is part of the neutrino dark matter story. So in the presence of the goldstone, you get new interactions, and that can be a way to also produce dark matter, right? So these right-handed neutrinos can annihilate into goldstones. Or if there are multiple neutrino species in the hidden sector, they can all interact with each other through the goldstone. And so you now have a new way of producing dark matter if you want, that is mediated by the goldstone, right? So this gives you new possibilities to produce dark matter, and you can plug in some numbers and you will see that for some values of the symmetry breaking scale, you get the right dark matter abundance. And that scale tends to be about 10 to the 5 GeV. Well, yeah. So if the symmetry breaking scale is 10 to the 5 GeV or lighter, then usually these goldstone processes are relevant for dark matter processes. You can also think about how the Majorana or how the goldstone decays in these kinds of models. And there are basically three distinct regimes, right? So in one regime, and that depends. So on the x-axis is the mass of the goldstone. So if the mass of the goldstone is very, very heavy, of course it can decay into all possible neutrino species, right? Including sterile neutrinos. And if it can decay into sterile neutrinos, which are quite heavy, then its decays can be pretty rapid because remember the coupling goes as the mass of the neutrino over the symmetry breaking scale. So if it's very heavy, it can be decaying pretty rapidly. So it would all decay before BBN and then it's gone. If it is at an intermediate scale where its mass is below the mass of the right-handed neutrinos, but above the mass of, say, dark matter, right? So if I imagine a neutrino sector where I have a dark matter, I have some other neutrinos, and the goldstone is somewhere in between, then it can decay into dark matter, but then it's a little bit slower because only one species is relevant. And so then its lifetime starts to get interesting. It can long live beyond BBN. But usually if it decays into a sterile neutrino, its lifetime is still shorter than the age of the universe. And so it cannot be dark matter. And then the third regime happens when it can only decay into active neutrinos. All of the sterile neutrino channels are suppressed. And in that case, it can actually be dark matter because its lifetime is so suppressed that its lifetime is longer than the age of the universe. So there are basically three distinct regimes that are of interest from the point of view of whether it decays before BBN or after BBN, or whether it can be dark matter. So those are the three regimes that are distinct for the goldstone. In the very heavy regime, when it's heavier than all of the sterile neutrinos, of course, whatever population of goldstones you produce can all go into dark matter, right? So it can be a way to produce dark matter. Let me skip the details because I think that's the main message. In the intermediate regime, where it's heavier than the dark matter, but lighter than some other neutrino species, this is the most interesting from the point of view of both BBN and from the point of view of seeing those neutrinos directly, because here it is possible that a heavy neutrino decays into a Majorana plus dark matter, right? So that is going to be the most abundant or the biggest branching ratio, and that'll be the dominant decay channel. And this is important because now this is a new channel for sterile neutrinos that is much faster than any other channel in the minimal sterile neutrino picture, which means that, so if you look at this plot, there are 3 different curves that are interesting. The blue curve is interesting because if the symmetry breaking scale is below the blue line, that means that the sterile neutrinos all have a new dominant decay channel, which is fully invisible. So all of these search channels that I told you about earlier, right, which try to constrain sterile neutrinos by producing them and looking at them decay into standard model particles, all of those would be irrelevant because now the sterile neutrino has a new decay channel that's completely invisible. So all of those searches would now have a different validity. And so direct searches are affected below this blue line. Below this red line, this new channel is relevant because it changes the lifetime so that the lifetime of the sterile neutrino is shorter than BBN. And so there are constraints on what the sterile neutrino parameter space can be. And there are some constraints on that due to the fact that sometimes they'll decay after BBN. So those constraints will be affected if you are living in a theory with a symmetry breaking scale below the red line, because all of the BBN constraints will now be different. And so those will be modified. And finally, there's this green line. And if you're living below this green line, there's actually a new channel where the sterile neutrinos, as well as the dark matter, can annihilate into goldstones very rapidly. And so the freeze-out story or the freezing story of the dark matter will be very different, and the relic density calculation will be affected. So the existence of a goldstone as part of this extended neutrino sector can modify, right, direct searches, BBN constraints, as well as dark matter histories. And finally, if the goldstone is so light that it is dark matter, or if it's so light that it doesn't decay into any of the sterile neutrinos, it can be very long-lived. So if it's extremely long-lived, of course, it can be dark matter. Even if it is not long-lived enough to be dark matter, its decays into neutrinos can affect dark radiation at BBN or at CMB if it's light enough. And the fact that it decays fully into neutrinos gives you interesting possibilities for neutrino telescopes, right? So you might be getting these exotic species that decay into neutrinos pretty late in the universe, even after BBN or after CMB decoupling. And so all these experiments looking for high energy neutrinos might find some exotic signature through this process. So I think I went through the goldstone story pretty quickly because I felt like I was running out of time. Are there any questions, confusions related to that? Otherwise, I'll show you my summary slide and then we can go back to discussions again. So to summarize, right? So from a theory point of view, if there are right-handed neutrinos, then their natural scale is close to the cutoff scale. So they prefer to be at the gut scale, which means if they are light, there's likely more dynamics in the neutrino sector. That explains why their masses are so small. One very natural way to explain this is to consider a hidden sector that couples to us through some heavy neutrino portal. And if there's a seesaw mechanism in the hidden sector, that explains why there are these light fermions in the hidden sector, which can act like sterile neutrinos at low energies. But if that is true, then there is this much more extended sector which has its own symmetries, right? And it has a Higgs particle, it has goldstones or gauge bosons, and you can motivate it through connections to other BSM scenarios like SUSY or twin Higgs or any other theory. And so this is a way to get dynamics at a heavy scale, namely the scale of split SUSY or something like that, and still get neutrinos, sterile neutrinos that are at a much lower scale, like the KeV scale or the GeV scale, or MEV scale. So from a theory point of view, that is very plausible. Experimentally, that means that now you can get new ways of producing dark matter, and those new ways will affect the distribution of dark matter that we would see today. Sometimes it can even give contributions to dark radiation, as I told you earlier, right? And there might even be other additional species that are light, like a goldstone, which might give you new decay channels for sterile neutrinos. And that would affect the direct searches for sterile neutrinos that we do at various detectors like DUNE. And this is also relevant for cosmology because that would also possibly give you additional dark radiation or more neutrinos after neutrino decoupling or interesting things like that. So I definitely haven't covered all of the different possibilities, and some of you already during the talk brought up new ideas that even I hadn't thought about. But yeah, this is what I wanted to talk to you about today, and we can of course discuss more. Thank you.
Okay, thank you very much for very nice talk and comprehensive. I think, yeah, you gave a very nice idea, the connection between small scale and heavy scale. Small.
Yeah, that was actually the most interesting thing to me, because usually when people try to build models for light neutrinos, you have to do new dynamics at a low scale, and that is usually the trouble, right? But this is a way to break symmetries at a high scale, but still end up with light strong neutrinos.
Okay. I think, yeah. Okay, now it's now open for questions. Yeah, feel free to ask a question.
Yeah, I have one question. Hello?
Yes?
Could you show page 20?
Page 20. Too much. Yes.
Yeah. If I remember, this looks like U mu n is not U mu n. So you say U EL.
Yes. So yeah, these curves are different depending on whether the right-handed neutrino couples to electrons or muons or tau leptons.
So you are saying this is UEN, probably.
Right. Yeah. And I just picked this as a sample. So there is a similar plot for U mu I or U mu n.
Yeah.
Which
it's
is
very
slightly
similar,
weaker,
but
right?
looks to me it's the numbers looks like U mu n, because it's about 1 GeV scale or 10 GeV scale. Between that is 10 to minus. In present, you are say 10 to minus 4. Okay, because from del P. Okay, as example, is let's say it's 4 GeV.
Right.
4 GeV. That is the like below MV B meson mass.
Right.
And then this only come from del P is actually from this is U mu L, U mu I in your case.
I see.
Because
yeah, I just took this plot from this paper, so maybe they had a typo.
I think so, because I mean, you know, it's like if it's UEL, is not only this coming from, but also neutrons direct decay.
Yeah.
That is much lower than this 10 to minus 4 at the stage of 534 GeV scale there.
I see.
So this must be U mu L, I think. U mu I in your case. You say I, okay?
Yeah. So no, that I think that perfectly.
Please check because it looks like typo to me.
Yeah. So this is this paper that is not mine, so I don't know what these people do.
Yeah. I have one more comments. The comment you are talking like something sterile neutrino portal, something neutrino is in middle.
Yeah.
So which connect hidden sector and or standard model sector. So it looks like good idea because this is why this is light, okay? Saying some pure GeV scale as example in your case. In lightest one was some KV scale anyway. But I mean the light not only come from such a model, but also like something slightly complicate scissors, like inverse scissors.
Oh, absolutely. Yeah, certainly.
Yeah. So you can give slight lighter like this way. So not without invoking some such a new beyond standard. I mean, this is all beyond standard model. Anyway, something new portal with a very high scale physics.
Yeah.
But that is also possible. But anyway, it looks nice. Idea looks nice to me.
Yeah.
Okay. Thank you.
Certainly. There are many different ways to get the light mass out without.
Yeah. I mean, like new MSM, like as you just introduced, you also introduced. That is, I mean, we don't know it is correct, but it's kind of phenomenological model from the bottom to up, not from top to bottom, as like you are saying from top to bottom, but just like from all the known like constraint, from low energy constraint, and also dark matter constraint, they just put it like this way, and then put like some scale in the GeV scale, the heavier one. So,
absolutely.
I mean, without invoking such some very high energy, some scale new physics, but it's also possible. Okay, anyway, I just want to give a comment.
No, certainly, those are very important things to keep in mind. And if anything, the story I told you today is a UV completion of the new MSM, right?
Yes,
so at low energies, this would look exactly like the new MSM. Yeah.
Okay. Thanks a lot.
Yeah, thank you.
Oh, one more question. Can I have your talk file?
Sure.
Yeah, I want to have it because it's quite interesting to me. I wanna dig into. I wanna go into more details.
Okay.
Definitely. Yes.
Talk slide. Yeah, from Bibhushan.
Okay.
I will send
you.
So,
Professor Hyunmin, can send me some talk file to me.
Okay. Yeah, it's great. Yeah.
Okay.
Yeah, Chung-Ang Kim.
Okay, thanks.
Do you know him? Chung-Ang, CS Kim. Bibhushan.
Thanks a lot.
Yeah, thank you.
Thank you.
Are there more questions? Some students?
I have a question.
Yeah, go ahead.
I think that the coupling between the standard model Higgs and phi is very small due to the vacuum expectation value of phi. So I just wonder that if phi can be formally produced enough to generate dark matter without infraton coupling.
So the mixing is small. That is certainly true, but at higher energies, right? So if your universe is at a temperature that's heavier than that scale, then you just have a quartic coupling, right? Which is lambda phi squared h squared. And if lambda is it doesn't even need to be that large. If it's bigger than 0.10 to the minus 6, I think, then the two will thermalize. Yeah, so that is not a problem. But like you say, at low energies, once you put in the BEVs, because the mass scales are so different, then the mixing angle is quite small.
Thank you.
I have a question. You have a nice mechanism for dark matter production with the hybrid UV freezing, IR freezing. You have a different phase space distribution depending on which one is dominant over the other one.
Certainly, I think.
Possibility depend. What is the origin of dark matter production?
So when you are driven by the UV, your typical interaction scale is just the temperature of the bath at that time, right? So when you redshift everything down, I think the average momentum of a dark matter particle is the same as the temperature of the visible sector. So it'll just be like a thermal freeze out, I think. The shape will be different for sure. I don't think the shape will relax to a maximal Boltzmann distribution, but the average temperature should be the same. Whereas for the IR dominant thing also, because the Higgs is part of the exotic Higgs is part of the thermal bath, and most of the decays are at temperatures above its mass, while when its abundance is not Boltzmann suppressed, right? So then I would also expect that the typical momentum of the dark matter would be about the temperature of the bath. So I think their average temperatures would be similar, but the shape might be different. We didn't look at that very carefully.
Okay. So, any more questions?
I have a very quick question. May I ask?
Please do.
May I ask a question? Okay. About the Goldstone scenario. In the second last page, you've shown the constraint for various scenarios, and I'm wondering, what about the ice cube constraint on a
Sorry, this one or?
Oh, no, the second one. No, next one, I guess. Yeah. So heavier goldstone case that will be affected by, well, constrained by ice cube.
Oh yeah,
Yes.
yeah.
Is it?
On this plot, we were just looking at how the standard properties of the heavy neutrinos are modified. But yeah, we weren't thinking about specific constraints on the goldstone in particular. But that's, yeah, no, that's a good point. And there will definitely be a constraint on how low the symmetry breaking scale can be from ice cube.
I see. All right, thank you.
Yeah, we didn't think about that.
Can I ask a question?
Yes.
So in your freeze-in model or mechanism, what would be the implication on current direct dark matter searches?
Oh, direct searches.
For example, you at some point I think you talked about the dark matter self-annihilation cross section would be very small, so that means
yeah. So that's the
produce enough WIMP dark matter.
Mm-hmm. Yeah, so that's sort of the unfortunate part of the story, that the signatures for dark matter are very suppressed, right? Because now you're not even relying on a mixing angle to produce them. So in principle, they're mixing with the standard model neutrinos can be basically zero. So they will never decay. So you would never see any X-ray lines, and they don't scatter off of nuclei that strongly. So you don't get any direct signals either. And so the most robust properties would just be these momentum distributions, if you could measure them, or if you're lucky, some contribution to dark radiation. But yeah, that was one of the sad things, that from the point of view of giving dark matter signatures, this was a little less promising.
Okay, thank you.
So in most cases, you consider global symmetry, right? So if you have a gauge symmetry, you may have G prime.
Yeah, the Z prime will be at the symmetry breaking scale though, right? So depending on what the gauge coupling is. Yeah, so if it's a PeV scale symmetry breaking, then you have a PeV scale Z prime, which you probably won't ever see. If the symmetry breaking scale is a little lower, if it's a TV scale or below, then maybe at the LHC you can see these things.
My question is, let's say, well, you don't have new charged fermions in your model, but if you have G prime and then the sterile neutrinos are charged on the G prime, you may have some, I don't know, could you have a dipole moment interaction for sterile neutrino?
Probably, yeah. I mean, I would imagine that they're as active as the Higgs in interacting with.
Then maybe if you, I don't know.
So then you would even get a thermal freeze-out. No, I see what you're saying. Yeah. So then, in principle, there's a big coupling, right? Not a feeble coupling.
And then
the gauge coupling is.
In the beginning of your talk, you mentioned that maybe sterile neutrino might be discovered by xenon 110 electron recoil. I mean,
did I say that?
We may have an explanation with a sterile neutrino for xenon 110 electron recoil energy. Can you realize correct coupling?
Yeah, I've
in your case.
Maybe not in this model. I think those require some special things. I forget what exactly. But I remember this idea, and even a few years ago, people were talking about seeing recoils of sterile neutrino dark matter. Yeah.
Okay.
Yeah, I don't remember the details.
Okay. Yeah. Okay. Are there more one or two questions from students, or I think that there are some students in the audience in my university.
Yeah, please ask anything you can think of, or say anything.
If you don't know anything, you can ask any question. This is the last time for your question. Last chance.
Last chance.
Today, the next week. I will invite you.
Yeah, yeah, and I'll be happy to answer questions over email at any time, of course.
Maybe.
Sorry, I have one question, but I
Perfect.
forget what was it. What only I have remember if it's on page 12.
Sorry, I think I missed your question.
So can I see page 12?
I'm sorry, I couldn't hear you.
Can I have see page 12? 12.
Page 12, okay.
Page 12, yeah.
Yeah, getting there, almost. I think I went too far.
Page 12. Yeah.
Sorry. It looks like I almost forget what was my question. Sorry.
Yeah, if you tell me what was on the slide, maybe I can reconstruct your question.
Okay.
Because I thought it was on 12, but it looks like not.
No, maybe let me see if it's one of the neighboring. Yeah, I mean,
Maybe you don't remember.
I cannot remember.
no, yeah, take your time.
Okay, yeah.
If you remember later, send me an email.
Okay, you can tell me later if you remember. Then I can ask Bibhushan your question instead.
But it must be something basic. So I think it can be. I can find some answer from internet because it was basic.
Sure, but yeah, don't hesitate to email me or ask him in also.
Oh, thank you.
Okay, yeah. Maybe just I can introduce my students, maybe.
Yes.
We can say goodbye.
So all the other people left.
You want to see my student? Maybe Eugene Kang. I think. I mean, maybe let me first introduce my my postdoc fellows. The Pinchu who asked many questions already during the talk.
You did, yeah.
Yeah. And then he's the postdoc fellow, and then also Yang-Wan Han. I don't know if you can see him.
No, I think the video is turned off.
Hi.
Hello.
Hey.